All right, let's jump right into this explainer. Today, we're setting up a totally mind-bending comparison that's going to completely reshape how you think about gravity, extra dimensions, and really the very fabric of our universe. We're going to contrast our familiar three-dimensional human universe with a purely hypothetical two-dimensional ant universe. Now, both of these universes are bound by the exact same speed of light, but here's the kicker. Taking away just one single spatial dimension changes absolutely everything. And the reason this matters so much, the reason physicists spend their entire careers obsessing over this flat 2D ant universe, is that stripping away a dimension actually uncovers the bedrock hidden rules of our own reality.
So what happens to the laws of physics if we trap a black hole in a two-dimensional universe? I know, it sounds like a totally absurd thought experiment, right? But this crucial question challenges literally everything we know about gravity, time, and the event horizon. You see, in our standard 3D world, a massive star collapses under its own weight and naturally forms a black hole. But in a 2D world, pure gravity is actually what physicists call locally flat. Think of space-time as a taut rubber sheet. In 3D, dropping a heavy bowling ball onto it creates a deep dip that pulls other objects in. But in 2D, placing a mass on that sheet creates no dip at all. Objects just slide right past each other without pulling on one another. There's no inherent gravitational attraction, no standard gravitational waves rippling through space. So if gravity doesn't even pull things together in two dimensions, how on earth could a black hole even exist for our 2D ant?
Well, looking here on the left, we've got the human standard 3D black hole, known as a Schwarzschild black hole. Geometrically, it forms this classic funnel shape, and its event horizon, the point of no return, is a two-dimensional spherical surface. But over on the right, we have the ant's 2D black hole, known as the BTZ black hole. Its horizon isn't a sphere at all, it's literally just a one-dimensional circular line. And because 2D space lacks that inherent gravitational attraction we just talked about, a black hole can't just form from a collapsed star. Instead, the BTZ black hole requires a negative cosmological constant just to exist. Basically, it needs the universe itself to possess this structural, inward-pushing curvature, acting like an anti-de Sitter cylinder, just to force the black hole into existence. The universe itself actually has to squeeze the mass together.
Section 1. When light leaves an echo. Breaking Huygens principle. So, taking away a dimension profoundly messes with how light travels through empty space. In our 3D universe, if you turn on a flashlight for a split second, the light travels outward as a sharp, clean flash. It's a perfect, expanding hollow shell of photons. This obeys what physicists call Huygens principle. But in the ant's 2D universe, because there's an even number of spatial dimensions, just two, Huygens principle completely breaks down. Light doesn't travel in a clean, hollow shell anymore. If an ant lit a match in this 2D space, the flash wouldn't just quickly pass over you and vanish. It would actually reverberate. It leaves this rippling ghost of light bouncing behind it, an echoing wavetail right inside the light cone. And when we map this out mathematically using a retarded Green function, the difference is just striking. That blue line right there represents our 3D space, a sharp, instantaneous spike representing that clean flash of light. It hits you and it's gone. But the orange line represents the 2D ant universe. Notice how it spikes and then kind of drags out over time? That mathematical drag has a beautiful, almost poetic consequence for black holes. It means that when an object falls into a 2D BTZ black hole, its final light doesn't just snap to black as it crosses the event horizon like it does for us. Instead, it fades elegantly as a long, echoing afterglow. The ant's black hole would visually fade out much more slowly and softly than ours. Moving on to Section 2, the great thermodynamic reversal, hot, cold, and specific heat.
Now, moving away from the strange behavior of light, we encounter a massive inversion when we look at how these black holes handle heat and mass. When we graph the Hawking temperature against the mass of the black hole, we get this really distinct X-shape. The pink descending line is our 3D human black hole. In our universe, black holes have what's called negative specific heat. I know, incredibly counterintuitive, but it means that as a 3D black hole gains mass and grows larger, it actually gets colder. But follow the blue ascending line for the 2D ant BTZ black hole. As it gains mass and grows, its temperature increases. It gets hotter, exactly like an object in our everyday experience would.
To put these features side by side here, we see the thermodynamics of these two universes are exact opposites. In 3D, temperature is proportional to the inverse of mass. This negative specific heat means a standard black hole sitting in a vacuum is thermally unstable. If it loses a tiny bit of mass to Hawking radiation, it gets hotter, which makes it radiate faster, losing more mass, getting even hotter, until it eventually evaporates faster and just explodes. But for the Ant's 2D BTZ black hole, temperature is proportional to the square root of its mass. This gives it positive specific heat. It's thermally stable. It won't run away and explode. It can actually sit peacefully in thermal equilibrium with a surrounding heat bath, totally defying our 3D logic.
Section 3. The perfect entropy match, connecting to the Carty formula. Now, this is where the 2D model transforms from a fun thought experiment into literally one of the most powerful tools in quantum gravity. Physicists wanted to know if they could calculate the entropy, the total hidden information, of the 2D black hole. So they calculated it using standard Bekenstein-Hawking geometry, which relies purely on gravity and space-time. Then they calculated it again using the Carty formula, which is derived from conformal field theory, a completely different framework based purely on quantum mechanics. And when they compared the two results, the ratio was exactly 1 to 1. 1.00000000000. It is an absolute monumental triumph in physics when gravity and quantum mechanics agree with this level of staggering precision.
Plotting the Bekenstein-Hawking entropy against the Carty entropy reveals a perfect diagonal line, with every single data point perfectly aligned. What this tells us fundamentally is that the total information of the 2D black hole is perfectly and entirely stored on its 1D circular boundary. The quantum states dancing on that one-dimensional edge perfectly describe the gravitational reality in the two-dimensional interior. The boundary dictates the volume. This flawless mathematical harmony is exactly what makes the BTZ black hole the ultimate laboratory for understanding how quantum mechanics and gravity actually unite.
And finally, Section 4, the holographic reveal. The boundary is the bulk.
So, all of this abstract math, the 1D boundaries, the exact entropy matches, it all brings us to a reality-shattering realization. The Ant's 2D world is not hypothetical. Our own horizon is an Ant's universe. Let's walk through this logic for a second. Our 3D human black hole has a 2D spherical event horizon. And thanks to the holographic principle, we know the information of everything that falls into a 3D black hole is etched directly onto that 2D surface. Therefore, the Ant's 2D universe structurally represents our 3D event horizon. The physics of the lower dimension exactly maps to the boundary of the higher dimension. The boundary literally is the bulk.
We've just seen how in Ant's 2D physics, where Huygens' principle breaks down into echoing light, where specific heat inverts to become thermally stable, and where entropy perfectly matches the Carty formula, can flawlessly govern the information on our 3D black holes. So, I'm going to leave you to ponder this final thought. If the surface of a black hole in our universe operates as a fully functioning 2D universe, and if our entire 3D reality can theoretically be described by a 2D boundary, what does that mean for us? Are we just a 3D hologram governed by a boundary and a higher dimension? Well, the math of the Ant's universe suggests it's entirely possible. Thanks for exploring this mind-bending concept with me today.